in the last classes, in the last two classes, we have introduced the classification algorithms in which are available in machine learning. Okay, so we have talked about uh, five different classification approaches. So which include predictive modeling, binary classification, multi-class classification, multi-level classification, and unbalanced classification problems. Okay, so today we will look into some classification algorithms which are heavily used in machine learning problems. Okay, so we can start from Bayes classifier. Bayes classifier. Then we will be talking about Naïve Bayes classifier, and then we will be talking about likelihood method. Okay, so before we start with Bayes classifier, so we will study some preliminary notations that we are going to use in Bayes classifier or other classifiers like Naïve Bayes classifiers, likelihood methods. So let us consider there is a sample space. There is a sample space, capital S. Okay, and there are two events that we can draw from sample space S. Okay, so if we draw two events A and B, then we can estimate the probability of an event A without having much information about the other event. Okay, or if we consider at class level, then we can say that we have been given the information about we have been given less information about some event than other event. Okay, or we can say that if we try to estimate the probability of an event without having much knowledge about the other event or other random variable, then we can get the probability of PA, either PA or PV. Okay, so this probability is known as marginal probability or distribution. Okay, so if we try to estimate the probability of event A without having much information about event B, then we can get this probability. Okay, and this probability is known as marginal probability. Okay, and when the events A and B occur simultaneously, then we can estimate the probability which is known as the joint probability. Okay, joint probability distribution. And when we estimate the probability of an event given other event, then we can get the conditional probability. Okay, so here we can write probability of A, probability of event A given event B. Okay, so this probability will be known as the conditional probability. Conditional probability. So with this initial assumptions, we can introduce Bayes classifier, and then we will be talking about the Naïve Bayes classifier. Okay. Now in Bayes classifier, suppose we have been we can have one of the two information about the data which is to be generated. Okay, now suppose the class labels are drawn from a known conditional distribution on the set of class labels 1 to C. Okay, so here we are having C number of classes. Okay, now C number of classes. Now the class labels can be drawn from a known conditional distribution on the set of class labels given the features. Now so this information can be interpreted as the probability of y at class C given data x, okay, or features x. We can say here x. So x so here the capital X is the feature vector, or we can say this is a data. So probability of y at class C given data x or feature vector x. So for C equals to small c equals to 1 to capital C. Okay. So here capital C is the total number of classes that are available in the population. Okay, or the distribution. So we can have so we can interpret the first information about a probability of y at class C given feature vector x. Okay, now other information we can have, like the class labels can be drawn from marginal distribution on class labels, and features are drawn from a known conditional distribution of features given the class information. Okay, now we can interpret this information as probability of y equals to, we can write c, okay, small c, and we can write probability of x given y at c, okay, or y equals to c. So for we can write small c equals to 1 comma 2 comma capital C here. So 1 to C. So as I said that the class labels, when the class labels are drawn from the marginal distribution on class labels, and features are drawn from a known conditional distributions of features given the class information, then we can write the probability of y equals to C, or we can say probability of y at class level C, and probability of feature vector x given y equals to C. Okay, now so we can let me write, this is equation 1 and this is equation 2. Now we can estimate the information about the probability of y equals to C given x from the, in terms of the probability of y equals probability of y at class level C and probability of x given y equals to C. Okay. Now if we obtain the former information in terms of the later information, then we can write probability of y equals to C given feature vector x equals to probability of x given y equals to c and probability of y equals to c and probability of x. Okay, now what we call this probability? Probability of y at c given x. So this probability will be called posterior probability. Okay, and this probability will be called likelihood. We will call this probability of x. So here we estimate the probability of features given y equals to c. Okay, so this probability will be called likelihood, and this probability will be called prior probability or marginal probability, or marginal we can say distribution, prior or marginal probability. Okay, and this probability will be called evidence. Okay, so this may be interpreted, this evidence, this probability, so probability of x is known as evidence, and this may be interpreted as the summation of all the probabilities. So we can, instead of writing probability of x, we can also write the summation over likelihood, which is multiplied by the prior or marginal probability. Okay, so if we further derive this base classification equation, then we can write the likelihood, which is multiplied with the prior probability or marginal probability, and in place of evidence, the probability of x, we can write the summation d equals to 1 to c, and summation over probability of x comma y equals to d. Okay, so here we get the summation over the joint probability distribution, probability of x comma y equals to d. Okay, so we take the summation over this joint probability distribution. Okay, so in place of this evidence probability of x, we can write the summation over this joint probability distribution. Okay, now if we further expand this denominator, which is the summation over this joint probability distribution, then we can get, so we can write probability of x given y equals to c, probability of y equals to c. Further we can write summation over probability of x given y equals to d, probability of y equals to d. Okay, now this is the Bayesian this is the Bayesian classifier where we estimate the posterior probability in terms of likelihood and prior probability or marginal probability. Okay, so in presence of evidence. Now with posterior probability, likelihood, prior probability, and evidence, so we can estimate the risks of the Bayes classifier. Okay, so how to estimate the risks of the Bayes classifier? So if the estimated risk is denoted by f cap x, okay, then we can write, or better to write first, risk R of C. Okay, so here R of C given X. That means we are trying to estimate the risks uh, of the class level C in presence of feature vector X. Okay, so this risk is the expected, we can have the expected loss. So we will multiply the expected loss with the posterior probability and we will get the risk of this Bayesian classifier. So we can write the expected loss L of y comma C. Okay, and further if we expand this loss function, then we can write d equals to 1 to C summation over loss function L of d comma C and posterior probability P of y equals to d given feature vector X. Okay, so here we are trying to estimate the risks of the Bayes classifier for a particular class C given feature vector X. So we can write d equals to 1 to C. So summation over L of d comma C, and in place of posterior probability, so what we can write the likelihood probability of X y equals to d. Okay, given y equals to d, prior probability P of y equals to C divided by summation over likelihood P of X given y equals to E, probability of y equals to E. Okay, so so here we use the different index E. So initially we use the index D for getting the posterior probability, and since we need to use the information of evidence in terms of the summation over likelihood and marginal probability, so therefore we can use the different index E for getting this summation. Okay, so we can say that the constant probability is the reciprocal of probability of X. So this will be given by over summation over probability of X given y equals to uh, D, from which is multiplied by marginal probability P of y equals to D. Okay, so so I can so here I can estimate the risks of the Bayes classifier in terms of the loss function and posterior probability, and if we further expand the posterior probability, then posterior in place of posterior probability we can we can have the likelihood and marginal probability, and which is divided by the summation over likelihood and marginal probability. Okay, so we can say the constant of proportionality is the reciprocal of probability of X, which is given by summation over likelihood and marginal probability. Okay, now once we get the risks, once we estimate the risks of the Bayes classifier, so now we need to minimize the function. minimize the Rix function. Okay, so therefore we can write a for f cap of x equals to, so here we are writing, so here c, small c belongs to 1 to capital C, so number of classes. Okay, so capital C is the total number of classes, and small c represent a particular class. Okay, and the for a corresponding datum x, if we try to minimize the Rix function, so we can write here arc mean of r. So r of c given x equals to small x. Okay, so here capital X is the feature vector. Okay, and small x is a datum. Okay, now for this datum, if we try to minimize the function or try to minimize the Rix function, then we can estimate the relevant parameters, and we can use those parameters value to find the find the Rix of the Bayes classifier. Okay, so here Bayes classifier classifies a new datum x as the class with minimum Rix. So here we get the minimum Rix by minimizing the Rix function, and we estimate the model parameters, which can be further used to get the minimized Rix for Bayes classifier. Okay. If you have any questions from this part, you can ask me. Now let us consider what we have made assumption about Bayes theorem, that in Bayes theorem, here each input variable is dependent upon all other variables. Okay. Now this assumption create a difficulty in calculation, or we can if we use this Bayes classifier on the assumption that each input variable is dependent upon all other variables, then sometimes we can face problem in calculation. Okay, now to remove this assumption, so we can consider each input variable is independent from each other. Okay, so here each input variable is independent from each other. Okay, now if we make this assumption without having the dependency of each input variable to other variable, then we can have another classifier. So we can improvise this Bayes classifier, and we can remove the earlier assumption on the input variable, which is found dependent upon all other variables. Okay, now we can remove this assumption, and we can write probability of a particular class given x1 comma x2 comma xn. Okay, and we can write, so this probability of a particular class given feature vector x1 to xn is given by probability of x1 given class information multiplied by probability of x2 given class information probability of xn given class information. Okay, so here we can clearly see that this probability of class given x1 comma x2 up to xn, so this is nothing but the posterior probability. Okay, and here probability of x1 given class information, which is multiplied with probability of x2 given class information. Okay, so these are the likelihoods. Now these likelihoods will be multiplied with, so likelihood will be multiplied with the marginal probability or prior probability which is estimated on the class. Okay, and this will be divided by the evidence, so which we estimate from the population. Okay, the population that we are studying. So this classifier is known as the Naïve Bayes classifier. So Naïve Bayes classifier. Naïve Bayes classifier. Okay. So in Naïve Bayes classifier, we make an assumption. We remove this assumption of the Bayes theorem, and we consider each input variable is independent from each other. Okay. So with this assumption, we estimate the posterior probability of each class when the feature vector x1 to xn are given. Okay. So this posterior probability is estimated in terms of the likelihood, which is estimated over the feature vector from x1 to xn independently when the class information is given, and these likelihoods are multiplied with the marginal probability, which is estimated over the class information. Okay, so which is known as probability of class, and this will be divided by the evidence, which is estimated over the population data. Okay, and this is called probability of p of data. Now if we see the advantages of Naïve Bayes classifier over Bayes classifier, then we can see that we can easily implement this Naïve Bayes classifier, and it will found to be efficient for many applications over Bayes classifier. Okay. Now we will be start talking about the likelihood methods. So now suppose the data from Cth class is randomly drawn from a distribution with likelihood probability of x given y equals to c. Okay, so on the sample space x, so if the sample space is given as capital S, then we can get the data from Cth class, which is randomly drawn from a distribution with likelihood p of x given y equals to c. Okay, now a likelihood classifier uses the training to estimate the likelihood of the we can estimate the probability p cap of y given y equals to c. So this p cap is the estimate of the likelihood probability of x given y equals to c. Okay, so the posterior distribution on the class can be estimated by, so we can write p cap of x given y equals to c. So p cap of x given y equals to c p of y equals to c. and we get the summation over likelihoods and prior probability. Okay, so we can write p cap of x given y equals to d and probability of y equals to d. Okay, so this is the estimate of the likelihood. Now if we see the different approaches of the likelihood methods, then we can have three different groups. So the first group of likelihood methods are called parametric method. Okay, so we will see some of the parametric methods, so which will come under likelihood methods. Okay, parametric method, non-parametric method, methods, and semi-parametric methods. Okay, so these are the classifications. These are the classifications of likelihood methods. So initial assumption that we make in likelihood method, that we need to estimate the probability of the likelihood which is which is drawn on the feature vector x when class information y is given. Okay, so probability of x given y equals to c. So from this likelihood we can estimate the probability p cap of feature vector x given y equals to c. Okay, so similar to the Bayes classifier, so we can get this likelihood in terms of uh, in terms of likelihood and marginal probability. Okay, so this likelihood basically nothing but, so this likelihood is nothing but the posterior probability. Okay, so we try to estimate this posterior probability from the given likelihood, and this will be estimated in terms of the likelihood p cap of x given y equals to c, which is multiplied with marginal probability p of y equals to c. Okay, and divided by the evidence. So in terms of in place of evidence, we can write the summation over likelihood and marginal probability. Okay, now if we classify the likelihood methods, we can have three different approaches of likelihood method. The one is the first type of likelihood method is called the parametric method. The second type of likelihood method is called the non-parametric method, and lastly we can have the semi-parametric method. Okay, now what are the parametric methods? What are non-parametric method? So in parametric method, we can have the quadratic discriminant analysis, linear discriminant analysis, and Gaussian mixture model, which is called GMM. Okay, quadratic discriminant analysis, linear discriminant analysis, and Gaussian mixture model. And in non-parametric, we will see the kernel density estimation, or in short we can write KDM, KDE, kernel density estimation, and histograms. Okay, and in semi-parametric method we have already discussed about the Naïve Bayes classifier. So Naïve Bayes classifier is one of the semi-parametric method. Okay, now why we call this algorithms like quadratic discriminant analysis, linear discriminant analysis, Gaussian mixture models are parametric method, and other are non-parametric method, and some of them are semi-parametric method. So so we can make an initial assumption we can make an initial assumption over the population that we are studying, and if we make assumption that the population or the data follows the normal distribution, then normal distribution, then we can get the parametric method. So basically here in parametric method the number of parameters are fixed. Okay, and here we make an assumption that the parametric methods follow the normal distribution, and we know about the normal distribution that normal distribution uses mean and standard deviation. Okay, mean and standard deviation. So these two model parameters. So using these two model parameters, we can estimate the density of a class. Okay, density of a class. So parametric method use the assumption that all such parametric method will follow the normal distribution, and here the number of model parameters are fixed. But in case of non-parametric methods do not follow the normal distribution, so we do not have any assumptions like the parametric method which follow the normal distribution. Okay, so here in non-parametric method the number of model parameters are not fixed. Okay, and we do not make any assumption like parametric method. But in semi-parametric method, uh, so we can use the both uh, uh, we can use the both parametric and non-parametric assumptions, and for in semi-parametric method. So in semi-parametric method, we can make assumption like parametric method, or we do not make any assumption like non-parametric method. That means here number of we can use some of the model parameters which are fixed, and some of the remaining model parameters which are not fixed. Okay, and in semi-parametric method, some of the data points may follow the normal distribution, and some of the data points may not follow the normal distribution. Okay, so we can start with parametric method, and firstly we will talk about the quadratic discriminant analysis. Now in quadratic discriminant analysis, we can estimate the probability of x given y equals to c. Then we can represent this posterior probability in terms, or we can estimate the likelihood in terms of normal distribution. Okay, so we can write p of probability of x given y equals to c. This is given by phi of x given model parameters mean and standard deviation. Okay, mean and standard deviation. So here mean and standard deviation, these two parameters are called model parameters. These two parameters are called model parameters. Okay, so this likelihood, if we here we are trying to estimate the likelihood. Okay, so in parametric method, or in non-parametric method or semi-parametric method, so you will try to estimate the likelihood. Okay, so when we estimate the likelihood in case of parametric method, we will use the information about mean and standard deviation. Okay, and this mean and standard so our objective is to we get the maximized function of the given likelihood, and in terms of this mean and standard deviation, and we will try to estimate the mean and standard deviation, so that we can get the maximum likelihood. Okay, suppose there are three distributions which correspond to three classes. Okay, so we get the distribution like this. So this is distribution A, distribution B, and this is called distribution C. Okay, now suppose we have been given an unknown example which is represented by this capital X, and we have to estimate the class density of this unknown sample. So how we can do that, or how we can estimate the class density of this unknown sample X? So we will take help of the parametric method. If we use the parametric method, then initially we have already made the assumption that the all parametric method follow the normal distribution, and here in parametric method the number of parameters are found to be fixed. Okay, so therefore we can write this likelihood in terms of normal distribution phi of X given mean and standard deviation. Okay, so we can write 2 pi standard deviation sigma c. So this 2 pi sigma c to the power half. Okay, and we can, this will be multiplied with e to the power half x minus mu c transpose. Then we can get this sigma inverse x minus mu c. Okay, so this is the classifier form. This is the classifier of form of the quadratic discriminant analysis. Okay, discriminant analysis. Now what we do, for each class C, the likelihood function is a Gaussian density function. So this likelihood function, since initially we have made an assumption about parametric method, therefore we can say that for each class C the likelihood function is a Gaussian density. Okay, so the Cth class density is estimated by mean and covariance matrix sigma, and training the density to estimate these parameters by given maximum likelihood. Okay, so what we are trying to do, we are trying to first we will estimate the likelihood in terms of the normal density function or Gaussian density function. Then we will try to estimate the model parameters mu and sigma c. Okay, so here mu is the mean. Okay, mu represent mean, and here sigma c represent the covariance. Okay, now in case of Bayes classifier and Naïve Bayes classifier, we have observed that when we estimate the Rix function, we need to minimize that Rix function. Okay, we have to minimize that Rix function. But here in parametric method, we will try to estimate the maximum likelihood. Okay, we will try to estimate the maximum likelihood in terms of the model parameters mu and sigma c. So here we are trying to get the maximum likelihood. Therefore we can write mu1 to mu c. So here mu1 to mu c is the mean over the number of C classes. Okay, and here we get the covariance sigma 1 to sigma C. Okay, so we are having C number of classes. So over the C number of classes, we will estimate or we will determine this mean and covariance so that we can get the maximum likelihood. Okay, so what we will write or how we will represent this maximum likelihood. So we can write this equals to, okay, so we know how to minimize a function, how to maximize a function. Okay, the same convention we will use in this case to get the maximum likelihood by maximizing this likelihood function. Okay, so first we estimate the likelihood of the uh, given example, okay, in terms of the class density, and then we will try to maximize it. So here we can write mu1 to mu c, comma sigma 1 to sigma c. Okay, so here I equals to 1 to c. Okay, so you get the familiar form when we estimated the when we estimated the posterior probability in case of Bayes classifier and Naïve Bayes classifier. Okay, so the similar form we will use in this case also. So when we maximize the likelihood function in terms of mean and covariance. Okay, so we can write here this represent the product over likelihood p of xi given y equals to yi. Okay, so here yi represent the label data and xi represent the data of a particular example. So this product will be estimated over this likelihood. So I equals to 1 to C. So here capital C is the total number of classes. Okay. So here we will get the product over this likelihood P of xi given y equals to yi. Okay. So further we can write alt max mu1 to mu c, comma sigma 1 to sigma c, product over C equals to 1 to capital C, and here I equals to 1, yi equals to C, and if we have n number of examples, okay, then this product is estimated over the likelihood P of xi given y equals to C. Okay, so here we get C number of classes, okay, and n number of we have n number of examples. Okay, now this product is estimated over this likelihood for n number of data points or n number of examples. So from this estimation we can determine the mean and covariance. Okay, and this covariance is determined in terms of the standard deviation and mean. So both these parameters are important to estimate the maximum likelihood of a class correspond to a particular example. Okay. Okay, so in the next class we will be talking about principal component analysis, linear discriminant analysis, and if time permits, we will be talking about Gaussian mixture model. So if you have any questions from this part of today's class, so you can ask me. Otherwise, we will stop now, and so we will have next class on Friday. If you want to ask any question, you can ask me. Otherwise, we will stop now. Okay, that's all for today.